let's go. So the previous side channel attacks I was talking to you about were all talking about, oh, I think I covered this, so let's skip this quickly. We were talking about cases where we have a victim, it's a box, it's a device, or it's a service running on web server, and there is an attacker, and the attacker is a separate lab setup, a separate, it's just, it's a dude measuring stuff or connecting stuff or cutting stuff. And when we're talking about microarchitectural attacks, our model is similar, but it's a little different. So if in the case of a side channel attack, a power analysis attack, we have an attacker box and a victim box, now we have an attacker process in the victim process. Okay, now these processes are running on the same machine, and let's say maybe the victim has some kind of secret. What kind of secret can you have inside this victim? Anybody want to write in the chat? Let's see if you remember something that we learned in class. What kind of secret can this victim have? Okay, they can have keys, right? All sorts of keys. Yeah, keys. Keys are a nice thing to see. What else can this victim have other than keys? Keys is like, okay, credentials. Okay, that's nice. So maybe there is a cookie, a session cookie stored by the victim that we can use to impersonate the victim. What else? What are the secret things can you try to steal from the victim? Let me try to focus you. Okay, sensitive documents. Okay, let's try to focus you. What if I'm not attacking the process, but I'm attacking the user who is actually interacting with the process? So what can I steal from the user? Okay, impersonating the user, that could be something. You want to steal the identity. So personal information. Okay, let me kind of continue with the class. I might want to steal, for example, the keystrokes of the victim. Okay, the victim is typing on the keyboard, and the attacker is getting these keystrokes. I might be interested in finding out the identity of the victim, of the user. If it's some kind of a super user, or user who's not allowed to interact with the computer during night, and it's the night. Another thing I might want to steal is kind of hints about the activity of the user. Is the user browsing to a certain website? Does the user have some kind of condition that might make it easier to extort this user? Maybe he belongs to some minority, or maybe this user has a medical condition that I might want to know as an employer, so I can fire this user before he dies, and I have to pay an insurance. Of course, that's illegal. Don't do that. But okay, so all sorts of information that can be about the user using the process. Another kind of secret is what is called the state. I want to steal the secret state. So maybe this process, anything we're stealing can be stolen. Yeah, of course, that's not relevant to this course. That's relevant to life. Might be things that are secret but are not keys. For example, a secret thing could be a random number generator state. Maybe this user is it's a gambling server, and I'm trying to get what is the next number the gambling server is going to output, so I can bet on this number and make some money. Or maybe it's some kind of internal the challenge response system, and I try to get the challenge, so now I can impersonate the response. So all sorts of secrets. So now, okay, the process one is got, let's say, just to make it easier to discuss in this hour, the process one has a buffer, array, and memory with the secret. So process two wants to get at this data, wants to read it out. So what is preventing process two from just, taking a pointer to this memory? It's on the same system, taking a pointer and reading out the memory of process one. Okay, so Elena says isolation, and it would be probably either Dimitri or Alex saying guest memory, virtual memory. Is this Dimitri this time? Hi, Dimitri. Hi there. Thank you for surviving until the week 8 of the course. there is some kind of what is called a trust boundary. The trust boundary means that the operating system, the virtual machine manager, the kernel, the CPU sometimes doesn't allow process one to process two, the attacker process, to get at the spy process. Why is that? What happens if you try? You can get, you can get an access violation or a segmentation fault, or you just get zeros, depending on the implementation of this isolation. So the system is defending processes from getting at each other's data, finding out which code it's running and what data it's accessing. And now this isolation is in several layers. So processes can be isolated, but also there is user isolation, right? A user can't find out stuff about things that other users are doing. For example, in Android, each app is using, Android is this kind of variant of Linux. So each app is a different user. So apps can't find, for example, which files are opened by other apps. If I find out which files are opened by another app, I might be able to spy on it and try to figure out what it's doing. Where is it connecting? Because a network connection is also a file in a sense, it's a socket. So there's isolation. And of course, there is another degree of isolation, the kernel, which holds all the secrets of the system. Right. Okay. Let's not go into ways it's broken. I'm talking about, the architecture. So the kernel has also sorts of secret data, functions that but only it can run, the passwords in plain text, and all sorts of secret stuff. And of course, user processes cannot access the kernel. And if we continue even further, there is could be a virtual machine system, and a virtual machine. All of these processes, including the kernel, think that they're running on their own hardware, but in fact, there are other virtual machines sharing the same hardware. So of course, VM1 does not even know that VM2 exists, even though they're on the same hardware. And does anybody know what this fellow is? What's the hypervisor? Anybody heard about it? Yeah, hypervisor is a virtual machine manager. It's like it's similar to the kernel in the system. It's the hypervisor is in the virtual machine system, so it can manage all the virtual machines. It can hide stuff from them and so on. So these are what is called trust boundaries. There are boundaries which prevent all of these protected processes and users and so on in VM from accessing each other. And this is what the architecture is implementing. Why? However, there was a problem. What is this problem? The problem is that all of these trust boundaries, all of these processes, all of these users, and so on, are running on the same hardware. Okay? This hardware is shared between all of these isolated processes. And if I understand what this hardware is doing, what this hardware is working, if I understand its externals, I can use the fact that this resource is shared to attack, to break this isolation. And now I'm using a definition of ACHMES in a paper you have in the Moodle. So microarchitectural attacks, they exploit deeper processor ingredients below the trust architecture boundary. So what is the idea? Two processes are perfectly isolated. There is no bug in the operating system, there is no bug in the CPU. But because they are using something deeper at the same time, there is some kind of leakage of data. And if I'm very creative and very clever and read a lot of papers, I can get secrets even though these processes are isolated. So this is a big model of microarchitectural attacks. And I want to tell you a little bit about the attacker model here. So the attacker model is a little different than the previous talks, previous weeks, and it also needs justifying. So the attacker model of microarchitectural attack assumes that the attacker is on the same machine of the victim as the victim. So let me ask you like a review question. If the attack and the victim are on the same machine, what's the point of the attack? They're on the same machine anyway. Okay, yeah. If we have two processes running on the same machine, right? So as Dimitri correctly said, just as I said a couple of seconds ago, there are isolations. There is isolation between two processes, two users, two VMs, even if it's on the same machine. So there is still very exciting stuff to be done, even if the attacker is on the same machine as it, a privileged installation. Okay. So now, if you can tell me, and you already wrote it in the chat, when can we justify this assumption that the attacker can run code on the same machine as the victim? So in what situations is this reasonable to assume? So, okay, Orel is saying a remote connection. Can you kind of develop that? What do you mean by remote connection? Okay. 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 So let's try to summarize. Just finish whatever you have on the keyboards and I'll try to summarize. Right. So one situation, which is a very, it's actually one of the places where microarchitectural side channel attacks were got very famous, is in the cloud setting. So what is the idea? I pay money to Microsoft or to Google or to Amazon, and they give me virtual machines somewhere on the cloud. And how do they make money out of this? They make money out of this because they give me and everybody else virtual machines. They buy a lot of hardware, and everybody's sharing this hardware. So Amazon, for example, can give me an instance somewhere in its data center, and it might give my victim another instance on the same machine. And of course, Amazon is trying to hide this from me. But there was a very, very nice work called cloud cartography, where actually it was a while ago. I guess things have changed, but the researchers were able to get an attacker and a victim reliably to run on the same hardware. So if you're saying if your victim is running on a cloud instance and you're very, very clever in finding a right way to place your attacker, you can run on the same machine as the victim. Okay, that's a good attack model. So you can attack servers this way. But you can say, as a system architect, I'm going to make sure that it doesn't happen to me. I'm going to use my own dedicated cloud. What other settings did you mention? Okay, so one of the things you mentioned was, let's see. Oh, okay. So actually, another environment which you might be using right now from home is a multi-user environment. So many people get remote access to what's called Amazon Workspaces, for example. So you run all sorts of apps on the server, and you're actually running as a terminal. For example, everybody wants to do their data mining, their deep learning on a powerful server. So you just connect to the server. And of course, now, as we learned 2 weeks ago, you might be very curious to find out about what other models other people are running on this server. So a multiple user environment is another way, another attack model. And the third one, which actually O.L. Lavi mentioned, no, who mentioned that? Let me scroll. Gil Fidel mentioned it. Gil Fidel mentioned it, is browsers. So what about browsers? If we think about it, a web browser is a machine that agrees to execute code sent by actually anybody on the internet. So you go to a website, you get the contents of the website, and you get some code to run, and you get an ad in the corner, and this ad also has some code you want to run. And then there's like a Google Analytics code that also wants you to run something, and the Facebook widget also runs something, and they're all using like Node.js, and they're using includes from 37 different places in the web, and everybody wants to run code on your machine. So the web browser is actually an execution environment. Now, this execution environment is constrained. There is what is called a sandbox. And the metaphor for a sandbox is, all these scripts are playing with the sandbox, playing in the sand, but none of the sand goes out of the sandbox. They're all isolated. But still, even though they're isolated, even though the language is very restricted, JavaScript, WebAssembly, very, very restricted, they're still running on the same machine as the victim. So attacks are still possible. So now this is one thing we can assume. So I hope I justify to you that it's reasonable in many cases to assume that the attacker is on the same machine as the victim. I just want to note, when we're talking about browsers, the victim is not the server, the victim is the client, it's the user sitting on the computer or whatever this user is doing. Okay. Now, another thing we need to assume for microarchitectural attack is that the attacker shares some resource with the victim. What does that mean? They're fighting, they're competing together to get at the same resource. And what that means is that if one of them, if the attacker got the resource, then the victim will have to, I don't know, to wait or to suffer. If the victim got the resource, then the attacker can measure it. So you can see that there is some kind of timing attack going on. So the victim causes the attacker to wait. So this is a timing attack. But this timing attack isn't just a one data point, the runtime of the entire execution. It's like a multi-dimensional timing attack. We can measure the action of the victim over time. So we get a lot of resolution, we get a lot of details. So in a sense, we can get the resolution that we get in the power analysis. So one thing I want to explain, what is microarchitecture? What does this term mean? So very hand-livingly, architecture means the stuff, the things that the user sees. So you really want to know, for example, what are the assembly language instructions that this computer that you're running on supports. You really want to know how much memory you have. You really want to know if you can access the network or not, and so on. The microarchitecture is stuff that the user shouldn't really care about, shouldn't really know. So you're saying you have 8 gigabytes of memory on your system. You should know that. You can't allocate more than that. But do you really care if you have 2 DIMMs of 4 gigabytes or 4 DIMMs of 2 gigabytes? No, you don't really care about that. Do you care if this memory is old memory or new memory? No, you don't care about it as a user. You run the same. Yeah, okay. You can run the same code and expect the same results. It doesn't really matter. And just an example, you have a wonderful application. Everything is running wonderfully. You shut off the computer and you change the microarchitecture. You install a software update, or you take out all the DIMMs and put in new DIMMs, and you turn on the computer and everything works as before. It might work faster or slower, but everything works as before. Because the microarchitecture, conceptually, it's not your problem. It's a problem of Intel, of AMD, of ARM, whoever is implementing your CPU. Not your problem, it's their problem. And here are some things which are shared resources between the attacker and the victim very commonly. So one thing that I'm actually going to talk about in the following 50 minutes is the cache. What is the cache? I will explain. The second thing is memory. So you have to access the memory, so you're sharing the memory. And you're sharing the connection to the memory, the path to the memory, and so on. You're also sharing ports. Now, ports is a little difficult to explain right now, but you know the CPU has cores, so the cores can run several commands at the same time, and each command is executed by a port. Hopefully next year, if there is nothing very special happening during the semester, I wish, I will be able to talk a little in more detail about ports and port smashing, which is cool. Instruction scheduling ports. Thank you very well. Thank you. And the last thing that they share is peripherals. So peripherals could be fast peripherals, like the GPU. There could be slower peripherals, like the disk drive or the network adapter, and so on. So if they're sharing these resources, they're fighting for these resources, then I can kind of think of doing some kind of timing-inspired attack. Fine.